you want to put a big field of solar panels, and now you want to pair it with a battery so that you can store that energy and deliver the electricity when you want. The problem is that the battery becomes more expensive than solar panels.
This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Potker. According to the Environmental Protection Agency, the energy sector is the largest source of greenhouse gas emissions. Our guest today is working to revolutionize energy technology. Asegun Henry is director of the Atomistic Simulation and Energy Research Group and professor in the Department of Mechanical Engineering at MIT. His work was recently recognized with an Alan T. Waterman Award, the nation's highest honor for early career scientists and engineers. Dr. Henry, thank you for joining us today.
Thank you for having me.
So I'd like to start with a little bit of the background, and I'm interested in knowing how you first got into engineering at all.
How I got into engineering was through a really good mentor of mine. His name is Dr. Mukola Abdullah. And he was one source of kind of a vision for me of what it meant to even be an engineer. So, growing up as a young black man, very many of us have never even met an engineer. So seeing somebody cool that was accessible, that was down to earth, started to put in my mind like, okay, this is what an engineer looks like. This is what an engineer does. So that's kind of one piece. The second thing I would say that triggered me actually getting into engineering was taking calculus in high school. I had a teacher. His name was Coach Mead. I believe he was actually an engineer as well. And the way he taught calculus is really what got me fascinated with engineering. And I'd always been a bit mechanically inclined. My father, there's a little bit of it that's a bit of DNA in the sense that my grandfather, carpenter, and my father was, he had always had an interest in fixing things. I spent a lot of time with my dad fixing things around the house. But really the connection with calculus was the first time that like all this math he'd been learning in middle and high school for the first time actually had like utility, like he could do something with it. And prior to that, and this actually ended up influencing very heavily my own teaching style. I learned, and what I got out of that experience was like that it's so important to tell students why the subject that you're teaching them is important. Like what is the value? What are you going to be able to do with it? You want to give that to them first, not after, but first. Lead with that. And then it actually makes the process of students learning the how or the what so much easier. Like I need to know why I'm doing this.
Right. The engagement and why it's related to anything they are interested in.
Exactly. And so this teacher, Coach Mead, he did such a phenomenal job of it. The calculus class I took with him was actually an entire year long. Many people, like when you get to college, it's just like one semester. But part of what the value of him having an entire year to teach it to us was like he took the time to really hype up a concept before he taught it to us. So I remember when he was going to teach us the derivative, like it was this mysterious thing. And he was like, this thing I'm going to teach you next week. Once you know this, you'll be within the less than, 1% of the population on Earth that actually knows what this is. And once you know what this is what you need to know to be able to put a person on the moon. Like this is the key thing that allows you to do all these things. And it's like, man, we're on the edge of our seat. And by the time we're like, what is it? Teach it to us, please. I want to know. And I distinctly remember one particular example probably did where it clicked for me. And I was like, okay, now I'm interested in this stuff. It was actually an example problem where he was doing a derivative and it was kind of a word problem, but he was calculating the answer to a question around a company is, I think, selling hamburgers or something like that. And if they sell the hamburgers at this price, they sell this many hamburgers. If they sell the hamburgers at this price, they sell this many. So calculate what is the best price for them to sell the hamburgers to make the maximum profit. And the light went off for me. I was like, whoa, you can, there's an operation you can do that tells you exactly what price does that maximizes your money. The idea that there was this utility to the process you were learning, all of a sudden I was like, okay, now I want to optimize everything. I was interested in optimization. I want to optimize everything. And that captivated me. And so that for me is where it kind of solidified, all right, I am interested in engineering, this idea that you can use math to actually tell you what you should do. to make decisions, real decisions that have real consequences, and you let the math guide you, then I was like, oh, this is unbelievably powerful and real. I got interested in it.
So how did that engagement guide you to thermal energy?
Yeah, the connection there is kind of interesting. I would say the connection there actually ties back to music. So in parallel with all this, I'm also a drummer. So I grew up as a drummer, playing African percussion. And as a percussionist, I was fascinated with vibration and sound. And I've watched the impact that can seem to have on people in a semi, maybe at least just their sense of self, their sense of well-being, hearing music. Even myself, I've experienced, you listen to some music that can affect your emotions.
Absolutely.
That was another piece of my personal experience that was real. It was intuitive for me. And for me, music and math became blended. So like how I would hear music, how I would hear music and see music. So I see the relationships, the ratios and the notes, the ratios and the tones. For me, those are mathematical relationships. I'm actually very fascinated intrinsically by that. And so my approach to music is kind of mathematical in nature. I don't think the music I create sounds mechanical or dry per se, but I get fascinated with the feelings that are associated with certain ratios. So for me, emotions and math and ratios are all intertwined. So then when I get to college and we start talking about heat and the idea that temperature is related to how fast atoms are jiggling back and forth, I got really intrigued by the idea, like, well, what sound is that making, right? Vibration at pretty much any level has certain frequencies associated with it. And what would that sound like? So the idea that this form of energy that is, of course, useful, important for all of modern life is intrinsically related to like vibration. And this other thing that I'm intrigued by, the marriage of that is what brought me really to the absolute nature of like the laws of thermodynamics. The idea that you can never break these laws, like you can't create or destroy energy, and it's an absolute thing. And I like absolutes. I like the idea that you can never get around this. And so these are the true boundary conditions of the universe.
I want to move into your thermal battery, the quote, sun in a box. Like, I love phrasing it that way. I think is really helpful for people trying to understand it. Can you talk a little bit about how it works? Like, what is it doing and what might it be used for?
Yeah, let me maybe start what it's used for. Its purpose is to take electricity off of the grid, specifically from renewables, store it so that you can hold it, and then put it back on the grid later when you want it. It's a buffering device. It allows you to hold it for some period of time. And the reason it exists, the reason you need it is because, and this maybe is a part that people don't appreciate. If you look at how the utility grid is actually operated, you have the places where the electricity is, I hesitate to say created because you can't create anything, but where it is converted, where energy is converted to electricity. And when that happens, the electricity exists and it goes straight along all the power lines and the wires directly to where it's used. There's no buffer. There's no place where it's stored in between. In fact, it's actually synchronized. The AC outlet, the 60 hertz at which the electrons are oscillating back and forth, that 60 hertz is the same frequency that the turbines are spinning at. It's 3,600 RPM. And there's a synchronization process where a turbine, as it comes online, has to synchronize with the grid, and then they're in sync. When you do that, there's no storage in between. There's no holding the energy. So what this means is that if you put solar panels out in a field somewhere or on your roof, when the sun is out, the electricity is available. If the sun goes down, there's no electricity. It's not held anywhere. Same is true for the wind. When the wind's blowing and that wind turbine is spinning, that's when the electricity is available. You don't get it another time. And so what a thermal battery is intended to do is take in the electricity when it's available, hold it, so that then you can decide when you want it later. And the way we do that, the way current batteries, the way many energy storage systems work, is they store energy in what's called an electrochemical reaction. They store it electrochemically. There's another form called pumped hydro. where you're storing it in the gravitational field. You're actually storing it with height. And in our case, we're using a fundamentally different means of storing energy, which is to store it thermally. And the reason we do it is essentially one key reason, which is cost. So if you want to put, let's say, a big field of solar panels, and now you want to pair it with a battery so that you can store that energy and deliver the electricity when you want, the problem is that the battery becomes more expensive than the solar panels are. And so what you primarily have to pay for is the battery. And so essentially there's a number of papers and studies that looked at this and looked at how low does the cost really have to get to in order for us to reach our goals. The goal we have to ultimately get to is a fully renewable grid where we're not even using fossil fuels anymore. And in order to get to that, you need the cost of the batteries to drop by like more than 10 times. Like it's not a little bit cost reduction. It's not some cost reduction that's going to happen because we do mass manufacturing of batteries. Like that's like that's like half the cost. So you can maybe get a third of the cost. We need more than 10. And so that requires a different technology. And so what we have invented is a different technology. And the way it works is we take in electricity and we run resistive heaters. So we have something that gets extremely hot. This is where this notion of a sun in a box came from. In many ways, it's actually not all that different in concept from fusion and all the excitement around fusion, right? Essentially, what a fusion reactor does is creates a small sun. It's trying to reproduce the reaction that happens in the sun on Earth. In our case, instead of trying to recreate the sun with now utilizing the same physics in the sun, we are taking the sun, converting it to electricity on Earth, now storing that electricity by making another object, a solid, super hot. It's about half the temperature of the sun. And we're putting our own sun inside of an insulated box. So we don't let the light out. It's got a bunch of insulation around it, and we keep that sun hot so that it cannot let its energy out. And only when we open a shutter and we open it up to allow the light out, that's when we get the electricity. And this allows us to control it. And we get the electricity when we want rather than just when the sun is shining or the wind is blowing.
Okay, so one point along the way to your development, you got a couple of Guinness Awards, Book of World Record Awards. I'd like to hear you explain that because that's not something everybody gets to have happen.
Yeah, there's a fun story behind that because this is truly a story of I guess maybe I'll call it triumph, in the sense that I kind of came to the table with what everyone termed, what everyone agreed was a crazy idea. You know, the basic idea I had was, let's just switch materials. Why are we so limited? Why are we just so married to metals? Why not instead look at ceramics? Ceramics can go way hotter than metals. No question about it. It's all known. It's well understood. The big difference is that ceramics are brittle. So ceramic is like your ceramic coffee cup or a ceramic plate. Everybody knows you drop it, it crashed, you know, it fractures very easily and cracks, and it's catastrophic. When it fractures, you can't use it anymore. It's no longer an old piece. Conversely, if you had a plate made out of metal, you drop it, no big deal. It gets a little dent. It's still functional. And this is one of the major reasons we try to make everything out of metal. It fails gracefully. It can take a hit, keep on going. But now when you're talking about highly engineered systems that do things that are really critical for society that we need to do, you open up the landscape and you say, okay, well, if it's highly engineered, I'm not intending on dropping it. I'm not planning on dropping it, actually. And maybe I should rethink and consider what would happen if I brought these materials back into the conversation. And what we basically hypothesized is, well, I think I can actually make an entire pump or a valve out of these brittle materials. And if I engineer it right so that I don't get these materials smacking each other, then maybe it won't break. Maybe I actually design it so it won't break. Even the fact that, like, if it did smack something, it would break and crack catastrophically. I won't let it. I'm designing it. It's mine. I get to choose how it's made, right? And so that was the basic concept. That was the basic idea is, and nobody could tell me there's absolutely no way it could ever work. It's just like, I don't think it'll work. Like, you know, because no one's ever done it.
Right.
And so that was the basic premise, and we did it. It took some years, and we figured out how to get it to work. We did crack some stuff, and we definitely didn't get it right the first time. But we figured out how to actually put brittle materials together to actually make a functioning system with moving parts. And there were so many, or a couple of occasions I'd never forget, with the students involved, where it was breaking, and they were like, let's just give up. Like, this is not working. Like, can we just move on to a different project? And had to give one of those like locker room speeches, like, we will win, stick with it. But it was very vindicating at the end to have it actually work, prove that it can work, and you just have to get it right. And so, when we went from there, then it's like, okay, well, this is a truly new record. It's a new thing, and you get contacted with Guinness World Records, and it's like, all right, well, we provide the data, and they wanted to see a published paper and stuff. They have these requirements, and that it becomes an official Guinness World Record.
Pretty crazy.
It was, yeah.
So you've now spun off a company, and I'm curious about. We've talked about, or you've hit on points talking about like planned obsolescence with materials and these kind of things. So I'm wondering about the kind of challenges with getting buy-in for the idea. And then I think within the answer to this, these two things will work together. And you're thinking about hooking into the existing grid. Like you talked about the turbines having to sync. What would be the difference that you need to hook this into the grid as we have it today?
For the most part, it's downhill from here. How this hooks into the grid isn't inherently really any different than the way a normal solar cell hooks into the grid. So this is still just PV hooking into the grid. The electronics that do it are essentially the same. I mean, the voltages, we actually can design what voltage we want it to be. Like, we have a lot of freedom. But we basically tie it to the grid just like a normal solar field. The difference is that we have actuators that control our solar panel, and with this shutter, right? We can control how much light we're seeing and modulate. We get to make the sun go down or come up in seconds. So we get to control it. But outside of that, it's essentially the same electronics, same way you tie in for a normal PV field.
So putting this all together, you're talking about doing things that matter, and really this, when it's online, will have a huge impact on climate change. Can you kind of talk us through some of that a little bit, like what difference it'll make compared to what we're used to now?
I mean, for me, it is an incredible source of pride and motivation to be able to wake up every day and feel like what I'm here to do is that important. This is, I mean, I'll use this as an opportunity to make a bit of a call to action. This problem, this issue, climate change, is, people say it all the time, but it's like, I like to say it in a particular way that hopefully makes people really pause and think about it. Like, the issue at stake is whether or not human beings will survive on this planet. That is the question. And we don't have an answer to it. We're not sure if it's too little, too late already. We don't know. We are in a state of emergency, trying to solve what is arguably the most important problem in the history of humanity. And it's not a question of whether or not there'll be trees or insects or plenty of other species will survive and outlive us. The key thing I think human beings need to focus on is, will we be here? And the way of life, the modern society, the modern way of life, inherently destabilizes our climate in a way that may not allow us to live here. And it's a race against time. And I don't know if I'm clear that we're not moving fast enough. What I don't know is whether or not we will move fast enough. And I implore, what is needed? I was really impressed. I enjoyed this movie Oppenheimer. because, as a scientist, you know a little bit about the Manhattan Project, but it was kind of nice to see it put on in a kind of dramatic fashion to really appreciate the significance of this whole notion of like the greatest scientific bet, and what the consequences are of either getting it right or getting it wrong. And the whole concept being that you bring the greatest minds on earth together, focused without caps on resources to just get it done. I think that climate change undoubtedly meets the same criteria. This is that level. This is an extinction level problem. And we need to throw at it the smartest, most brightest minds without restriction on resources to have a shot. There's no guarantee we will solve it in time, but to have a shot. And what I think comes along with this, and my call to action is, I think my suspicion is many scientists who don't currently work on anything climate related look at it as, oh yeah, there's some folks that work on that, and that's good. They should be working on that. And I work on this. And I would strongly encourage any scientists, technologists, whatever out there to literally consider, like, make the switch. The people who work on it decided to work on it. We need more people to decide to work on it. And that means putting down what it is, or whatever else you've spent your career working on.
Special thanks to Asegun Henry. For the Discovery Files, I'm Nate Podker. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.